Good evening. This is the last trip to Clinkerland, or at least the last set of trips to Clinkerland for Chapter 7, because we have 3 more videos that we got to go through, or at least 3 more concepts that we got to go through. We might have an extra optional video somewhere along the way, just for extra examples. But nevertheless, what we need to cover in Section 7.7 are these 3 things. We need to talk about how you use the second derivative test, when it's possible, because it's not always, in order to find relative minimum and relative maximum values. We also need to learn how to find the absolute extrema of a function on a closed interval. And we need to use all these techniques that we've been learning for finding extrema in order to solve what are called optimization problems. Alright, let's get right into the second derivative test. And what I want to do is start by relating the second derivative test to the first derivative test. And you'll hopefully recall that the point of the first derivative test was to determine when did you have a relative minimum and a relative maximum, if either, for the graph of a function. And the way the first derivative test would work is we would see where does a function switch from increasing to decreasing, or vice versa, by noting the changes in the sign of the derivative of the function. So for instance here, since the function changes from decreasing to increasing, since the first derivative changed from negative to positive, we knew that there was a relative minimum. Then the first derivative changed from positive to negative when the function changed from increasing to decreasing, so we had a relative maximum. And of course, you know that then the first derivative changes back from negative to positive on this graph, which meant that there was a second relative minimum value. Okay, first derivative test used to determine where the relative extrema of a function are. And I bring that up because that's exactly the goal of the second derivative test. Although the process for using the second derivative test is a little bit different. It's truly a little bit more simple when it works. It just does not work 100% of the time. Okay, now reason this with me. We're going to have relative minimum or relative maximum values wherever the first derivative of a function is equal to 0. That you understand. So for this graph, at x equals negative 1.5, at x equals 0, and at x equals positive 1.5, that's where that's where we can have a relative maximum or relative minimum values. Okay. That part is the same as the first derivative test. You have to find the critical values of a function anytime you're trying to find relative extrema. But here's where the second derivative test is different and in fact simpler. Rather than having to plot that little number line that you're used to making, where we have to put all the critical values on that number line and then find out what the sign in each of the intervals created by those critical values is, what we can do instead is this. We can simply see at each critical value is the graph of the function concave up, because if it is, you're going to have a relative minimum value, such as here and here. Both those critical values have concavity up there. Or is that critical value a point where the graph is concave down? And if so, that means that you've got a relative maximum value. Or in other words, we can see, is the second derivative positive or is the second derivative negative at each of these critical values, such as is summarized in this picture from your textbook. Alright, and this little set of pictures is not necessarily from the graph that I created, though it can be related to it. Okay, now it says if f double prime of c is equal to 0. Whenever it says c, what we're referring to is a critical value. And so if you plug in a critical value into the second derivative, and the second derivative is positive, then f has a relative minimum. And you can see from that graph there the function was concave up at that critical value, so there's a relative minimum. And then of course, if you plug in a critical value c into the second derivative and it gives you something less than 0, if the second derivative is negative at that critical value, then the function is concave down, and that would mean that f has a relative maximum value, as you can see from the picture to the right. Okay, so second derivative test, plug in the critical values of a function into the second derivative and see if you get if the graph is concave up or concave down at those critical values. Now here's this summarized again with a picture from your book. But there is one other thing I need to talk about before we actually try some examples. Okay, now you can pause and kind of read about the second derivative test, but number 3 in here in particular we're going to have to discuss. Again, when it's talking about a value c, it's talking about a critical value. And I can justify that by saying it's telling you that if f prime of c is equal to 0, if the first derivative of some value equals 0, that's when you have a critical value. And if the second derivative of the function exists near that value c, then if the second derivative of that critical value is positive, f has a relative minimum. I put a check there just because we talked about that already. If the second derivative is negative, then you have a relative maximum at that point. But what we haven't talked about yet is, well, what if the second derivative is neither negative nor positive? What if you can't define the concavity of the graph at that critical value? Well, if the second derivative is 0, it's neither negative nor positive, then the second derivative test fails, and the first derivative test must be used. Okay, so there are some instances where the second derivative will equal to 0, in which case the second derivative test doesn't tell you whether you have a relative or maximum or minimum value. Let's go ahead and start applying this to some actual equations. All right, what we need to do is in order to use the second derivative test, we need to find the first and second derivative of this function f of x to begin. All right, pause and go ahead and do that, and then we'll continue. And then once you've found the first and second derivatives, the second derivative test still requires us to find out where the critical values of a function are. So we still need to set the first derivative equal to 0. In order to find those critical values. Now if you go ahead and solve that critical value by, or that equation with the first derivative by factoring, you're going to find out that x equals 0 and x equals 3 are the critical values. Now what the second derivative test is going to allow us to do is it's going to allow us to substitute those critical values into the second derivative to determine if the function is concave up or concave down at those points. Now I'm actually going to start with x equals 3 to begin with, and there's a reason, and you'll see very shortly what the reason is, but it was fine to start with 0. If I find out, I'd rather state it this way, if I plug in 3 into the second derivative, well, that's going to give me 108 minus 72, or 36, which is greater than 0. In other words, the second derivative is positive at that critical value. And since the second derivative is positive at that critical value, that means the graph is concave up there, and so that means that there's a relative minimum when x equals 3. All right, now I would rather say the exact coordinates of the relative minimum value, and so I would plug 3 back into the original function in order to determine this. And what you would find is that the relative minimum would occur at 3, negative 25. All right, so we have one relative minimum when x is equal to 3. Now, what about when x is equal to 0? All right, well, we said that we're going to plug in all the critical values into the second derivative. And so let's go and do that. If we plug in 0 into the second derivative, we're going to have 12 times 0 minus 24 times 0, we're going to get 0. Now remember, that means that the second derivative test is inconclusive, because the function is neither concave up nor concave down at that point, and so we can't say that there's a minimum or a maximum value. And if there's neither a minimum nor maximum value there, at least according to the second derivative test, then we need to use the first derivative test to determine, well, which is it, if either. All right, so let me do that real quick. All right, remember with the first derivative test, you just care about what the sign of the first derivative is at either side of a critical value. So we would make our little chart where we're showing the signs of f prime of x, and we would put our two critical values here. Only one of them matters this time. And we would find out, well, if x is less than 0, is the first derivative positive or negative? And if you take something like -1 and plug it in, what you're going to find is that the first derivative is negative over that interval. Then if you pick something between 0 and 3, and it has to be between 0 and 3 for this to work, that's the only reason I put the 3 here. Say you plug in 1 into the first derivative, well, that's also, it turns out, going to give you a negative value. So this function is decreasing until it gets to x equals 0, and then it's decreasing again. Do you see how you can't define the concavity because that's concave up on one side and then it's concave down at the other side? That's the reason second derivative test failed. And it turns out that point is neither a relative minimum nor a relative maximum. So we already have our answer here. We have a relative minimum at the point 3, -25. Now, did you still have to check to see whether x equals 0 was a relative minimum or maximum when the second derivative test failed? Yeah, you needed to check. There are times where it could still be a maximum or a minimum value. All right, but it did turn out that it was neither in this case. All right, got two more examples, and basically what's going to happen with these two examples is you're going to work them out. You're going to check your work with mine. All right, so we're not going to spend a whole lot more time listening to me. You're doing a whole lot more work on your own for the rest of this video. There you see the next function that we're working with. I want you to go ahead and find the first derivative and the second derivative, find the critical values of the function, and plug them into the second derivative to see if you have relative minimum or maximum values. And if you have to use a first derivative test because the second derivative test is inconclusive, do it. Go ahead, then check your work. All right, there's the work. You see the critical value, only one here, was x equals 3. When I plug in 3 into the second derivative, it gives me -2. In fact, anything would because the second derivative was a constant function. And then since the second derivative was less than 0, since it was negative, that means the graph was concave down at that portion. And if the graph is concave down at a critical value, that means you have a relative maximum at that value. And that relative maximum then would be at the point 3,9. Good work. Got one more for you to try. Sandra, you do the work here. The differentiation is just a little more complicated because you got to use the chain rule, but not too tough. See what you get. All right, look over my work, and I'll write the conclusion out here. I didn't show the work for the derivatives, but those are the derivatives that you should have gotten that you see on your screen. The critical values were 0 and positive and -3. When I plugged 0 into the second derivative, I got a negative value, -36 to be exact. When I plugged in positive 3 and -3 into the second derivative, they both gave me 72 precisely. What the point is that they're positive though. And so, since the second derivative was negative at x equals 0, that critical value was a relative maximum value. And since the second derivative was positive at the other two critical values, that means those two were relative minimum values. So the conclusion is what you're going to see on your screen right now. Remember that the y-coordinates for the maximum and minimum values come from plugging in those values into the original function, not into the second derivative. All right, second derivative just determined their maximum or minimum values. Great. Well, I would recommend looking at your graphing calculator and the graph to see that this is accurate. You'll have to change your window settings to accommodate that 81. Nevertheless, good work. See you next time.